In this video, we'll be looking at a second method to add water across an alkene, and this is called oxymercuration-demercuration. So an alkene can be converted to an alcohol using oxymercuration-demercuration. If we have an alkene, it can be treated in the first step with mercury 2 acetate. So the OAC, this is the acetate ion, and then water THF, these are just the solvents. The intermediate after this step is not isolated, and instead it will then undergo a second step, which is a sodium borohydride reduction. So overall, this is electrophilic addition of mercury 2+. We're doing an oxymercuration, and then in the second step, it's a demercuration. So using these conditions, ethylene can be converted to ethanol. If we have an unsymmetrical alkene and we carry out oxymercuration-demercuration, we will get the Markovnikov product. So oxymercuration-demercuration proceeds with Markovnikov addition. So what's going on in this reaction? You're not responsible for the mechanistic details, but I want to go through it so that you can understand where the selectivity comes from. With mercury acetate, we have mercury, and it is connected to two acetates. Now, usually when we're thinking about a metal and a nonmetal, we think about ionic bonds. Well, it gets a little bit more complicated because there are some metals that have more of a covalent bond. So that's why I'm drawing it this way. So mercury has a lone pair of electrons, but since oxygen is pulling away electron density because it's so electronegative, the mercury will have a partial positive charge, making it an electrophile. So our electron-rich alkene can share electrons with the mercury, pushing away one of the acetate groups as a leaving group. But because mercury has a lone pair, mercury can share back some electron density with the other alkene carbon. So this is analogous to what we saw with an alkene reacting with X2. So our carbon is still connected to the other carbon by a sigma bond. It's still connected to the hydrogens, but this carbon shared its electrons with mercury, and then mercury shared its electrons with the other carbon. And mercury has a positive charge. This intermediate can then react with water, and water can add to the face opposite the mercury. In this case, it's symmetric, so it doesn't matter whether it adds to this carbon or this carbon, but it must add to the opposite face. So let's say it adds here, opening this up, giving us this intermediate. Water has added here, still has one lone pair and a positive formal charge. Over here, we have our mercury, and it has a lone pair that used to be shared between the mercury and the carbon. And then after another molecule of water can grab off a proton, that gives the product of the first step, the oxymercuration. So we get this. Then with sodium borohydride, we have BH4-. This is a source of hydride. This is going to add to this carbon, kicking out the mercury. So we have two of our hydrogens that were originally present, and we have a third hydrogen that came from the borohydride. leading to our final product, an alcohol. So the oxymercuration leads to this, and then the demercuration leads to the alcohol. So if we look into a little more detail at the oxymercuration-demercuration, if we have an unsymmetrical alkene, we will form as an intermediate the cyclic species, and then when water adds, what's the difference between these two carbons? Because this carbon is connected to only hydrogens, whereas this carbon is connected to a carbon, this can better bear the positive charge. So this ring will be skewed, leading to a small partial positive on this carbon, but a bigger partial positive on this carbon. So when water adds, it will add here to the more substituted carbon. So I'm not going to show all of the steps, but that is going to lead to the mercury over here, and then the OH over here. And then on step 2, sodium borohydride, that will add another hydrogen here, get rid of the mercury, and so we end up with the Markovnikov product. So this is very similar to what we saw when we looked at the reaction of an alkene with bromine in water, for example. But the important thing is that here we end up with a hydrogen adding to the alkene carbon that originally had more hydrogens, giving us the CH3, and the OH becomes connected to the other alkene carbon that originally had fewer hydrogens, giving us the OH at this position. Now we can also think about the stereochemistry. So our intermediate, let's say the ring forms on the back face. Then when water adds, it will add to the front face, and it will add to the more substituted carbon. So that's going to push the methyl group back, open this up. So the methyl is now back, and water will be here. Well, the OH, the alcohol, will be there, and the mercury will be here. And then after step 2, we will end up with this. So in the end, because we are adding a hydrogen, we really don't care about the stereochemistry, but we do get anti-addition leading to the trans product. But since this is just an intermediate, we don't really care. So Markovnikov addition of water by oxymercuration-demercuration. So in converting an alkene to an alcohol, we have two different methods to carry out this reaction. We can use acid catalyzed hydration, or we can use oxymercuration-demercuration. So in both cases, we get the Markovnikov product. So that is the exact same. With a small molecule, this is pretty easy to do. So why would we use this much more complex set of conditions? Well, this is fine on a nice small simple molecule, but they are pretty harsh conditions. And so if we have a complex molecule that has a bunch of different functional groups, some of them might be sensitive to these conditions. And so having the oxymercuration-demercuration as an alternative can be a good thing. Furthermore, because of the mechanism of the acid catalyzed hydration, so keep in mind we are going to form this carbocation, and if water adds, we will get this. But if this rearranges to give a tertiary carbocation, then we are going to get this as our product. So with acid-catalyzed hydration, we have the risk of carbocation rearrangement. Whereas with oxymercuration-demercuration, because there's no carbocation, there is no risk of carbocation rearrangement. And so this is the exclusive product.